Okay, we're going to talk about Chapter 9 now on bonding. And with this chapter we explain how and why atoms attach to each other. We explain why some combinations of atoms are stable and others aren't. For example, why is water H2O? Why isn't it HO or H3O? One of the simplest bonding theories was developed by Gilbert Lewis. It's called Lewis theory. And it emphasizes valence electrons to explain bonding. And using Lewis theory, we can draw models called Lewis structures or electron dot structures that allow us to predict many properties of molecules, such as molecular shape or polarity, solubility, reactivity, acidity, and basicity. So it's a very useful model. So why do atoms bond? Well, chemical bonds form because they lower the potential energy between the charged particles that compose atoms, the electrons, which are negative, the protons in the nucleus, which are positive. And these processes are spontaneous if they result in a system with lower potential energy. The potential energy between charged particles is directly proportional to the product of the charges and inversely proportional to the distance between the charges. We talked about that already in Coulomb's law, where potential energy equals 1 over 4 pi epsilon. But the thing I want you to notice is the term Q1 times Q2 divided by R. That's the product of the charges divided by the distance. So for charges with the same sign, potential energy is positive and the magnitude gets less positive as the particles get further apart. For charges with the opposite signs, electrons and protons, for example, potential energy is negative and the magnitude gets more negative as the particles get closer together. Remember, the more negative the potential energy, the more stable the system becomes. Now, for you physics folks out there, you might have stumbled upon Coulomb's law before, where it's shown as a force that is inversely proportional to the square of the distance, r squared, but energy is force acting over a distance, so the unit r, not r squared, is correct if you're talking about potential energy and not force. So we see in this graph, plotting potential energy versus distance, r, that the repulsion between like-charged particles, two electrons for example, increases as the particles get closer together. They get closer, the energy goes up. But for charges which are opposite, an electron and a proton for example, we see that as the particles get closer together, the potential energy is lowered. So we're going to look at three kinds of bonding in this unit. We're going to look at ionic bonds, which occur between metals and nonmetals, and where electrons are transferred from the metals to the nonmetals. We're going to look at covalent bonds, which are bonds between nonmetal atoms and electrons are shared. And we're going to look at metallic bonds between metal atoms where electrons are pooled. Now when metals bond to nonmetals, some electrons from the metal atoms are transferred to the nonmetal atoms. Metals have low ionization energy, and it's relatively easy to remove an electron from metal atoms. Nonmetals have high electron affinity, and it's relatively easy to add electrons to them. Let's take a look at how sodium chloride is formed from its elements sodium and chlorine gas.
When a piece of sodium metal is added to a flask of chlorine gas, the vigorous reaction that takes place releases a lot of energy, and sodium chloride, common table salt, forms. The chemical details of sodium chloride formation are similar to the formation of many other simple ionic compounds. Let's view the process of ionic compound formation on the atomic scale. As soon as the metal and nonmetal make contact, the process begins. When the chlorine molecules land on the sodium surface, they separate into individual chlorine atoms, each lying next to a sodium atom. Focus on one pair of atoms to see the key event in the formation of an ionic compound: electron transfer from the metal atom to the non-metal atom. The sodium atom has 11 protons and 12 neutrons in its nucleus, and 11 electrons around the nucleus. The chlorine atom has 17 protons and 18 neutrons in its nucleus, and 17 electrons surround it. The sodium atom transfers an electron to the chlorine atom, and the particles that result attract each other and release energy. The loss of the electron converts the sodium atom into a smaller positively charged sodium ion, Na+, while the gain of the electron converts the chlorine atom into a larger negatively charged chloride ion, Cl-. Let's view this essential step once more. This electron transfer process occurs between all the other sodium and chlorine atoms as well. The large quantities of energy released vaporize tiny clusters of ions, and these attract others to release more energy. These clusters, which eventually aggregate and coat the walls of the flask, consist of the regular array of ions that make up crystalline sodium chloride.
So what we saw was that the sodium atom, 1s2, 2s2, 2p6, 3s1, transferred its valence 3s1 electron to the chlorine atom, 1s2, 2s2, 2p6, 3s2, 3p5. And in doing so, the sodium became the sodium ion and ended up with a stable noble gas configuration, 1s2, 2s2, 2p6, and chlorine became the chloride ion and ended up with a noble gas configuration, 1s2, 2s2, 2p6, 3s2, 3p6. The potential energy of the system dropped when sodium and chlorine reacted to form sodium chloride. Okay, the steps involved in the formation of an ionic compound from a metal and a nonmetal are worked out in something called the Bourne-Haber cycle, and there are 5 different energy steps involved in this transformation. We start with sodium metal as a solid and chlorine as a gas. The first thing that has to happen is that the solid sodium vaporizes to sodium gas. So that's energy number 1. The second step is for the chlorine molecule to break apart into the chlorine atom. That's the second endothermic energy involved. The third step is for the sodium atom to ionize, to lose its valence shell electron and become Na+. That's the third endothermic step. So we have 3 endothermic steps now. And we're at the top, and we can begin to look forward to some energy payoff. The electron is taken up by the chlorine atom to become the chloride ion. That's the electron affinity of chlorine, and it's an exothermic process where energy is released when the chlorine atom takes on an electron. The biggest exothermic step occurs when the sodium ion as a gas and the chloride ion as a gas come together to form a crystalline lattice structure, sodium chloride. That's a huge amount of energy that is released. So 3 of these steps are endothermic, 2 of these steps are exothermic. But whether the whole process is exo or endothermic depends, as in any state function, on the initial step and the final step. The energy of the initial step is right here with solid sodium and chlorine gas. The final step, the energy of the sodium chloride, is lower, and therefore this process is exothermic. This is a net exothermic process. Energy is released when sodium and chlorine react to form sodium chloride. Now we're going to talk about a concept which is not in your textbook, so listen up. It's called charge density, and we're interested in it because of its relationship to lattice energy. Lattice energy, as we saw, was the biggest single exothermic step in the formation of sodium chloride. So what does that have to do with charge density? The charge density of an ion is the ratio of its charge to its size. And of course, the size is proportional to the atomic radius. So the higher the charge of an ion and the smaller its size, the higher is the charge density. The higher the charge densities of positive and negative ions that form an ionic bond. The stronger the bond, the higher its lattice energy. The energy released when gaseous ions combine to form a crystalline lattice. So I'm going to ask you this in class, giving you this graph of trends in lattice energy. Here's a series of positive cations, all of +1, and a series of anions, all of -1, and the lattice energies for each of the compounds that they can combine to form. And what I want you to think about is how to relate these energies to the charge densities of the particles making up these compounds. And which compound would have the highest lattice energy of, say, these 5? And which would have the lowest charge density of these 5? Okay? So we'll talk more about this in class, but you should be able to answer these questions. Which salt would have the greatest lattice energy of these 5? And I'm going to ask you that in class too. All right, let's take a look now at another kind of bond formation. That's the covalent bond formation.
We shall consider the bond in the simplest molecule, hydrogen. This apparatus permits us to introduce H2 molecules into a discharge tube to convert them to hydrogen atoms, and then study the regeneration of hydrogen molecules. After adjusting the gas flow, the voltage is turned on. In the glow region, the bonds in the H2 molecules are broken to form atoms. We know hydrogen atoms are there because their characteristic colors of light are emitted in the glow region of the tube. This light emission is caused by high-energy collisions with electrons. As the gas flow carries the hydrogen atoms beyond the discharge region in the tube, the atoms no longer glow. In the path of the hydrogen atoms, we've placed a piece of fine platinum wire. We see that where the atoms strike the wire, it becomes white hot. Heat is being released. In animation, we can see how chemists picture what is happening on the platinum surface. Hydrogen atoms strike the surface and sometimes become bonded to it. When two hydrogen atoms approach one another on the surface, they can bond to each other and form a hydrogen molecule. The platinum has acted as a catalyst, and it is heated by energy released as the molecules are formed. The net reaction is H plus H gives H2 accompanied by the release of energy. A chemical bond is formed. Chemists explain this bond formation in terms of the electrostatic interactions between the electrons and nuclei in the two atoms. Looking again at the interactions between the two atoms as they approach, we can record graphically the total energy, plotted as a function of the proton-proton internuclear distance, r. When the hydrogen atoms are widely separated, the energy is just that of the left-hand atom, E sub h, plus that of the right-hand atom, again E sub h. The sum for two isolated atoms is 2 E sub h. As the atoms approach, their potential energy becomes lower, like that of a ball rolling down a hill. At the equilibrium bond distance, the potential energy is lowest. If the atoms are forced into shorter distances, repulsion dominates and the energy rises rapidly. The atoms separate again and seek the position at which the energy is lowest. We have now a model that explains the bonding between the simplest kinds of atoms, hydrogen atoms. A chemical bond forms because the energy is lowered as the atoms approach. The lowering of the energy results from the simultaneous attraction of each electron to two protons. Let's pass helium through the same apparatus we used earlier. When we turn on the voltage, again, collisions with electrons cause the helium atoms to emit their own characteristic light while they are in the glow discharge region. As the gas flow carries the helium atoms over the platinum wire, we see that the platinum wire is not heated. We see no evidence of energy release. In helium, therefore, the attractive forces do not dominate over the repulsive forces sufficiently to hold the atoms together. Calculations show that if two helium atoms approach, the energy is lowered very little and only at quite long distances. Quickly, the repulsions become dominant and the energy rises. The atoms separate and no chemical bond forms.
So as two hydrogen atoms approach each other, what we see is that the attractive forces increase between the electrons and the protons of both atoms. And the energy begins to fall to a minimum, to a low energy state as energy is released, as these attractive forces between electrons and protons are maximized. And finally, they are at this equilibrium bond distance. If the atoms try to get any closer, the repulsive forces quickly take over between the positive charges in the nuclei, and the atoms are forced apart. So now we have a stable covalent bond between the two hydrogen atoms. So now we're going to talk about bond dipole moments. A dipole moment, expressed as mu, the Greek letter mu, is a measure of bond polarity. Now, a dipole is a substance that has a positive side and a negative side. And if we assume a compound is 100% ionic, we can calculate its dipole moment as follows. Mu, the dipole moment, equals Q, which is the electrical charge that's involved, times R, which is the distance between these electrical charges. Now, this is not Coulomb's law. If you remember Coulomb's law, there was an inverse relationship between the charges and the distance. In the dipole moment calculation, there's a direct relationship between charges and distance. The units that we use to express dipole moment is the dBi. Now, if a measured dipole moment of a substance is less than this calculated value, we can calculate the percent ionic character of the bond, which is simply the actual dipole moment divided by the theoretical dipole moment, calculated using the formula above, times 100%. So, as an example, let's say the dipole moment for compound XY is 3.5 dBi. And the bond distance is 130 picometers. What is the percent ionic character of this XY bond? So here's our formula. Mu equals Q times R. Q for each unit of charge, that's the charge of a proton and the charge of an electron, is 1.6 times 10 to the minus 19 coulombs. Now let's find the dipole moment of this bond if it were 100% ionic. So Q equals 1.6 times 10 to the minus 19 coulombs. R is 130 picometers. Plugging that into our formula, we get 1.6 times 10 to the minus 19 coulombs times 1.3 times 10 to the minus 12 meters, and that equals 2.1 times 10 to the minus 29 Coulomb meters. If this bond were 100% ionic, and our mu, our dipole moment, is 2.1 times 10 to the minus 29 Coulomb meters, let's see if we can convert that into debye. 1 debye equals 3.336 times 10 to the minus 30 Coulomb meters. So if we convert this dipole moment to debye units, we get 2.1 times 10 to the minus 29 Coulomb meters. Divide that by 3.336 times 10 to the minus 30 Coulomb meters, and we get 6.3 debye. So, if the bond between X and Y were 100% ionic, its theoretical dipole moment would be 6.3 debye. However, the dipole moment for compound XY was actually measured to be 3.5 debye, not 6.3. So let's calculate now the percent ionic character. Percent ionic character equals 3.5 divided by 6.3 times 100%, and that equals 56% ionic character. So here's another problem. And I'm going to ask you this one in class so you can see if you can do it, and then you'll be all ready when we tackle it in class. The dipole measured for hydrogen iodide is 0.380 debye, and the bond distance is 161 picometers. What is the percent ionic character of this hydrogen iodide bond? So use the formula, we plug in Q and we plug in R, we calculate then the debye units for the theoretical as if it were 100%, and then we actually use the measured value of it, 0.380, to calculate the percent ionic character of the bond. Dipole moments are affected in electrical fields. Here are molecules with a dipole that are between two plates. The plates are not charged yet, and you can see there's no organization to the direction in which the molecules are pointing. As soon as you turn on the electrical current, so one plate is negative and the other is positive, the molecules align themselves so that the positive side is toward the negative plate and the negative side of the molecule is toward the positive plate. Dipoles are directly affected by electronegativity, which is the ability of an atom to attract bonding electrons to itself. Electronegativity increases across a period from left to right and decreases down a group from top to bottom. So fluorine is the most electronegative element. Francium is the least electronegative element. Noble gas atoms aren't assigned electronegativity values because they don't form covalent bonds usually. And it's the opposite of the atomic size trend. Here's the deal. The larger the difference in electronegativity, the more polar the bond. And the negative end is toward the more electronegative atom. Now, the concept of electronegativity was developed by Linus Pauling. He looked at the bond energy of hydrogen gas, 436 kilojoules per mole, and he looked at the bond energy of fluorine, that's 155 kilojoules per mole. And he reasoned that if hydrogen fluoride were purely covalent, and the hydrogen and fluorine were equally sharing their electrons, then the bond energy of hydrogen fluoride would be about the average of 436 and 155, or 296 kilojoules per mole. But in reality, hydrogen fluoride has a bond energy of 565 kilojoules per mole. Pauling reasoned that an unequal sharing of the electrons between hydrogen and fluorine would give the compound more ionic character and make the bonds stronger. He then developed the electronegativity scale, arbitrarily assigning fluorine the highest electronegativity value of 4, and based electronegativity values of other elements on comparative bond energies. So again, here's the periodic table. Electronegativity increases. Easy way to remember it, as you approach fluorine, electronegativity increases. Fluorine is the most electronegative element in the periodic table. So if you have chlorine molecule, then there's no dipole, because the chlorine atoms have exactly the same electronegativity. But if you bond hydrogen to chlorine in a covalent bond, those electrons in that bond are not being shared evenly. Chlorine has a higher electronegativity value, it's 3.0. Hydrogen is 2.1, which means that in this bond, chlorine attracts these bonding electrons more than does the hydrogen. And because the electron density around the chlorine is greater than around the hydrogen, chlorine has a partial negative charge. You'll see this little squiggle a lot. It's a delta, lowercase Greek letter delta, meaning partial. Partially negative charge on the chlorine, partially positive charge on the hydrogen. Now, if there's an even greater electronegativity difference, say between sodium ion and chloride ion, sodium is 0.9 in its electronegativity value, chloride is 3.0. Now you have a bond which is effectively ionic. So it's the electronegativity difference that can tell you whether you're dealing with a purely covalent bond, as in the case with chlorine, or a polar covalent bond, as what happens when hydrogen bonds covalently to chlorine, or an ionic bond. You have a sodium ion bonded ionically to a chloride ion. Here's a graph that shows electronegativity difference and percent ionic character. We see that lithium fluoride, which has an electronegativity difference a little greater than 3, is almost 100% ionic. And as the difference in electronegativity between the bonding elements gets smaller, the percent ionic character of those compounds diminishes accordingly. So with hydrogen fluoride, with an EN difference of 1.8, it is not even 50% ionic character to its bond. And as we slide down even further, iodine monobromide has very little difference in electronegativity between the iodine and bromine, and almost no ionic character to it. This chart enables us to assign a designation of ionic, or mostly ionic, or purely covalent, or polar covalent, based on the difference of electronegativities. And here's the table. If the difference in electronegativity is greater than 1.7, we call that compound mostly ionic. If it's between 0.4 and 1.7 in difference of electronegativity values between the bonding elements, we call that compound a polar covalent compound. If it's less than 0.4, it's mostly covalent, and if there's no difference in electronegativity, so you have two elements like hydrogen bonding together, it is completely, purely covalent. So which bond has the most ionic character? I'll ask you this in class. And which compound would have the least polar or the most covalent character? I'll ask you that in class too. Now we're going to talk about Lewis structures. Atoms bond because it results in a more stable electron configuration and a more stable system with lower potential energy. And they bond together by either transferring or sharing electrons. Usually this results in all atoms obtaining an outer shell with 8 electrons, the so-called Octet Rule. But there are plenty of exceptions to this rule. Usually, in starting out, we're going to say the key to remember is to try and get an electron configuration like a noble gas. Now, in drawing Lewis structures, we have to be able to count valence electrons. And for the main group elements, the group number equals the valence number of electrons. So for the first group, the alkali metals, those are S1, and there's 1 valence electron. The alkaline earths, beryllium, magnesium, etc., 2 valence electrons. Boron, aluminum, gallium, the third group, 3 valence electrons. Fourth group, 4 valence electrons. Nitrogen, phosphorus, arsenic, 5 valence electrons. Oxygen, sulfur, 6. The halogens are going to be 7 valence electrons. Fluorine, chlorine, bromine, etc. Rarely do we work with the noble gases, but if we did, they would have 8 valence electrons. So let's try our hand now at writing Lewis structures. Let's do the Lewis structure for methane, CH4. The first rule is to find the central atom and surround it with the outer atoms. Usually, the atom with the smaller electronegativity value is the central one. But methane is an exception because hydrogen is never the central atom. It can only have one bond going to it. So it wouldn't be a very good central atom. So in this, we're going to take our carbon and surround it with 4 hydrogens, and then connect each hydrogen with 1 bond with a dash. And that dash, and every time we write a dash, that represents 2 electrons being shared between the 2 atoms. Now, the second rule, sum all the valence electrons. Since this is not an ion, we do not have to add 1 for a negative charge or subtract 1 for a positive charge, because this is a neutral atom. So here we go. Carbon has a valence of 4, hydrogen has a valence of 1, and there are 4 of them. So that's 4 times 1 is 4. So our total number of electrons is 8. Now, rule 3, subtract 2 electrons per bond from the total to get the sprinkle number. In other words, of these 8 valence electrons, I'm using 8 of them right now in bonding hydrogen to carbon. Here's 2, 4, 6, 8. So I'm going to subtract from the valence, I'm going to subtract 8. I have 0 to sprinkle anywhere. And this molecule is done. This is the Lewis structure for methane. Now let's try one slightly more complicated, the chloride ion. So first, let's write out the central atom. That's going to be the chlorine. It has a smaller electronegativity value than oxygen. And oxygen usually is going to be a peripheral atom. Not always. It isn't in water. But the rule holds here. Chlorine's the central atom, and we put in an oxygen around the chlorine like this, and we add one single bond between each oxygen and chlorine. Now we're ready to start counting electrons. We sum all the valence electrons, and if an ion, we add one for each negative charge. Well, it is an ion, it's an anion, so we have to add one. Let's see now. Chlorine has a valence number of 7. The negative charge has 1 extra electron, and there are 3 oxygen at 6. So that's 18, isn't it? So total, that's 26 electrons altogether that we have working for us. Now, we're going to subtract in Rule 3 2 electrons per bond that we already have used to connect oxygen to chlorine. That's 2, 4, 6. So we're going to subtract 6 to get our sprinkle number 20. So our sprinkle number is 20. So we're going to start sprinkling in pairs of electrons, first around the peripheral atoms, then any extra go onto the central atom. So here I go. 2, 4, 6. That's 1 oxygen. 2, 4, 6. 2, 4, 6. And notice that each oxygen is completed with an octet of electrons around it after I add those electrons to it. I now have added 18 electrons. I have 20 to add. I've added 18 of them. So I'm going to add 2 electrons to the chlorine right here. Can't see that very well, but there's our pair of electrons on the chlorine. And now that has an octet of electrons as well. Now let's try our luck with sulfur dioxide, okay? Sulfur is the less electronegative atom, so it will be in the center. Oxygen around it. Here's an oxygen, here's an oxygen, and we know there's going to be at least 1 bond going to them, so we put those in. Now, we sum all the valence electrons. It's not an ion, so I don't have to add any or subtract any because it's a neutral molecule. The valence number of oxygen is 6. The valence number of sulfur is 6. It's in the same group as oxygen. So that's 3 times 6. And that is going to be 18 valence electrons. I'm going to subtract from that the 4 electrons I've already used in these single bonds between oxygen and sulfur. There's 2 and there's 2. So I'm going to subtract 4. And that's going to give me 14 electrons. That's supposed to be a 4. 14 electrons to sprinkle. That's my sprinkle number. I put them in around the peripheral oxygens first. 2, 4, 6. 2, 4, 6. That's 12 that I've added to the oxygens. I have 2 more to add. I'm going to put that on the central atom right there. But the sulfur, now I've used up all my valence electrons, but sulfur in the drawing that I have is not obeying the octet rule. It only has 6 electrons around it, not 8. So in this situation, where I'm not getting an octet of electrons around the central atom, I'm going to take a pair of electrons that's situated just on oxygen, a lone pair, and move it over so that it shares with sulfur. And when I do that, I will end up with this. I'll end up with a double bond to this oxygen. This oxygen, whoops, that's a pair of electrons right there. And this oxygen also has its 8 electrons. Now you can see that every atom is obeying the octet rule. This oxygen has 8. The sulfur now has 8. 2, 4, 6, 8. And this oxygen has 8. So that is the Lewis structure for sulfur dioxide. So let's draw the Lewis structure for the sulfate ion, SO4 2-. Sulfur is our central atom, so we'll write sulfur and put 4 atoms of oxygen around the sulfur, and we'll put a single bond between each oxygen and sulfur, like that. Remember, this has a 2- charge, so those 2 electrons have to be counted. Now we're ready to sum all the valence electrons. Sulfur is 6 and each oxygen is 6. So that's 6 times 5 is 30, isn't it? And we add 2 for the 2 negative charge. So that's 32 total electrons to play with. I'm going to subtract 2, 4, 6, 8, which are already on the diagram. So that is going to give me 24 sprinkle electrons. So here I go. 2, 4, 6, 2, 4, 6, 2, 4, 6, 2, 4, 6. 6 times 4 is 24. There it is. I'm done. This is the Lewis structure for the sulfate ion. Okay, let's try carbon dioxide now. Carbon is central, so we'll put in carbon right here, right in the middle. We'll put an oxygen around it and another oxygen, connect them with single bonds. Now I'm ready to add my valence numbers. Oxygen is 6, carbon is 4, that's 10, oxygen is 6, so that's 16 overall electrons. This does not have an ionic charge, so 16 is the total number. I'm going to subtract 1, 2, 3, 4 because they're already being used from the 16. So that leaves me a sprinkle number of 12. So I'll put 6 on this oxygen and 6 on this oxygen. That's 12. Are we done? No, we're not. Why? Because carbon isn't obeying the octet rule. It only has 4 electrons around it, 2 here and 2 here. We have to get carbon to have 8 electrons around it, and the only way we can do that is to take electrons which were just lone pairs on selfish oxygen and start to share them with the carbon. And we'll do that with 2 pair. So that when we're done, carbon will have a double bond. The oxygen will have only 2 lone pairs instead of 3, and the same thing on the other side. Oxygen, and then double bonded, and then only 2 pair of electrons. And now oxygen has 8, 1, 2, 3, 4, 5, 6, 7, 8. Carbon has 8, 1, 2, 3, 4, 5, 6, 7, 8, etc. So this is now the Lewis structure for carbon dioxide.